Good afternoon, everybody. Welcome. My name is Scott Mara. Welcome back to the PATH seminar. And it's my distinct pleasure this afternoon to introduce Dr. Larry Klein. So Dr. Larry Klein is someone that I'm just getting to know now, but looking at his background and anticipating his talk, someone who seems to have been have the mentality of PATH for many, many decades. So it's really a pleasure to, learn more about you and your work. Short bit about Dr. Klein. So well recognized within the traffic management community for expertise in evaluating and specifying sensors for traffic management, particularly in sensor data fusion. Spent over 40 years in everything from project management, sensor and communications experience to ITS and data fusion applications. Skills include architecture development and evaluation, advanced detector system specifications, data processing, including data fusion, system integration. I understand that you receive honor from US FHWA on multi-year detection technology for an ITS project. You have 8 books demonstrating and sharing technical knowledge around sensors, data fusion, I imagine many of which with transportation applications, authored over 50 technical papers, presentations on ITS architecture development, performance in modern traffic sensors on freeways, surface street sensor, data fusion applications, from defense to traffic management, overlaps with a strong history in PATH related to, for example, PEMS that was invented here in PATH. And I'll also recognize comes to us through a nice connection through Professor Dave Atwood, who is in material science and engineering, and also affiliated with the engineering science program that I also run in another hat that I wear. So thank you, Dave, for connecting us, and thank you so much, Larry, for coming. Pleasure to have you with us. Thanks.
Thank you, Scott. Thank you. It's a pleasure for me to be here, and I thank you folks for inviting me. I've been dealing with traffic sensors since the 1990s, and it started with a federal highway program while I was working for Hughes Aircraft in Fullerton. They won a contract to evaluate new types of traffic sensors, and I was the program manager. So we set up sites in 4 different cities, and I got to see quite a bit of the country, but at the worst times of year, like we had in test the sensors in cold weather. So I spent winter in Minneapolis, spent summers in southern Florida, and in Phoenix and Tucson, things like that. If you have any questions as I go through this, please feel free to ask them. Let's see. Oops. Am I pushing into the wrong one? Oh.
If you want, maybe you can just say next slide and listen.
Next slide.
Yeah, there we go. Perfect.
There we go. So I'm going to talk about traffic sensor applications to signal control and to vehicle and incident detection. I am not going to talk about way and motion sensors or road weather sensors or other types of sensors. There's just a lot to go through. There are various ways that people classify traffic flow sensors. One of the ways is shown here. There are those that are mounted in the roadway and those that are mounted over the roadway. Sometimes the in-roadway sensors are called intrusive sensors, and the ones mounted over the roadway are the non-intrusive ones. The types of in-roadway sensors that I'm going to talk about are the inductive loop and the magnetometer. and the types of over roadway sensors are video detection systems, microwave sensors, of which there are two types. One is presence detecting radar, which can detect stop vehicles, and the other are Doppler sensors, which detect moving vehicles. And then I'm going to talk about LiDAR and its applications, and give you some examples of how that's being used. There are a couple of sensors that employ combinations of sensor technologies, and I'll show you some examples of those. The types of benefit, that was a summary of my presentation. The types of energy that are detected by these sensors fall into the electromagnetic, acoustic, and ultrasonic realms. Okay, one of the questions that I frequently get is, how do you make the choice? What type of technology would you like to deploy? And there are questions that you have to ask yourself, and your answers will serve as a guide for you. What types of data are you looking for? What are the types of vehicles or other objects on the roadway or the sidewalk that you want to detect? Can the sensor give you the data you need with the required accuracy and confidence interval? You should take into account the life cycle cost of the sensor. So not just the purchase price of the sensor, but the cost of software upgrades, installation, training, maintenance. What's your agency culture? There are some agencies like the Washington, DC DOT that don't want to mount overhead sensors on their historic roadways and bridges. What's the quality of vendor support? And then there are still other questions. If you're looking at overhead sensors, is there a way to mount them available, or will you have to install mounting? If you're looking for the in-road or the intrusive type of sensor, what's the condition of the roadbed? What's the weather and climate like? And what are the data transmission options? So the first of the sensors that I'll talk about is the inductive loop detector. Typically on a freeway or a limited access highway, they are used to measure presence, speed, count. On the freeways in California where they're installed, they're put in what's called speed traps. There are two loops about 6 feet apart, and you can get a pretty good measurement of vehicle speed that way. They are also used to actuate traffic signals. The passage of a metal vehicle over an inductive loop will decrease the inductance of the wire loop, and that decrease in inductance is sensed by the electronics unit or the detector in the roadside cabinet, and it knows that some metal object has gone over the loop. Loops are fairly accurate if they're properly installed and they're maintained. For each of the senses, you'll see a summary slide like this. This is the one for the loop. On the top are the typical output data that you could get from a loop: count, presence, lane, occupancy, average vehicle speed. It's most accurate when you use two loops. And with one loop, you can assume a vehicle length, and there's a way to calculate vehicle speed, which again is not as accurate. The advantages of the loops: they have low per unit costs. The technology is well understood, and they're pretty well standardized. Loops come in different shapes for different applications. Some of the limitations are you have to interrupt traffic for their installation and repair. They are susceptible to damage by heavy vehicles or utility repair. And the reliability is a strong function of those who install. When I was doing the federal highway job and working in Florida, Florida DOT and the state police closed a section of a freeway for us to install fresh loops, which is very nice. But the contractor that they used was a bit lazy. And he knew from past experience that if he blew the debris out of the saw cut and, to get it clean so the debris wouldn't cut the wire and the sealant would stick well, then the excess sealant would stick too well to the roadway, and it was hard for them to scrape it off the roadway. So they never blew out the debris from the saw cuts. And I brought that to the attention of the DOT. And at the time, they didn't do much about it. But my advice is to an agency: if you're putting in loops, have an inspector out there, make sure that it's being done right. As you may know, there's a dual loop card available that has the ability to classify vehicles. It puts out a high frequency up to 100 kilohertz signal that energizes the loop, and with it you can get imagery of the metal undercarriage of a vehicle, which differs from car to pickup truck, to 18-wheeler to bus. And it's possible to classify vehicles that way. And I've got a video that shows you that. Oh, look, it's starting. Wonderful. So you can see the objects. I'm afraid to push something on here. So that's the truck, and that's the signature on the right of that type of truck. That's a tanker, and it has a different signature. There's another truck, and it's characterized by its own signature again. This started out as a federal highway funded device, I think through the IDEA program. You can see the double peaks from the two.
Is the signature also sensitive to the material?
Metal, so it has to be a metal,
Like will different metal alloys with a different signature or the different?
I don't know, I wouldn't think so. You can call the manufacturers, they're pretty nice and helpful.
Okay.
Yeah.
So can you re-identify vehicles?
Yes.
And how accurate is that?
Maybe on, okay, if I go back. Let's see if there's some here. Classification 90 to 95% accuracy. But there could be a hitch with those numbers. You'll note there's no confidence interval.
Mhm.
So is that a 1 sigma number, a 2 sigma?
Right, cause I'd be
When you were
wondering,
saying re-identification, just want to be clear, my understanding, and please tell me if I'm off base here, is pretty darn good with classifying vehicle types. So pickup truck, passenger vehicle, et cetera, et cetera. But like, it's not gonna be able to distinguish between an Audi and a Mercedes.
Right, sure. True.
Yeah, and I honestly, it's been a while, but I forget exactly how good is it at distinguishing between a sedan and a crossover? That I'm not sure.
right, but I'd be curious how that degrades as like traffic conditions change if you're in congestion. But that's where the error bars.
Is it based on the loads, like, the PSI, the truck? is
I would
always-
think if the undercarriage height was too great, that the signal
Yeah,
would degrade. Because I know when you put in loops, there are guidelines for how high the undercarriage is, for how many coils of wire or other features of the loop need to be adapted. You can find those in the traffic detector handbook.
Your experience with Florida DOT, were they using inductive loop detectors for classification actively, or this was a feature they weren't?
There are, I don't know if Caltrans is using these in some places. You can see that it might have toll road applications. Or it might have way in motion applications.
Yeah.
Load limits on a bridge.
Right? You could estimate weights.
Well, by the type of vehicle, well,
Exactly,
it could
yeah.
be empty or full going.
True.
But it's basically, I'm not sure, well, one of the applications is states need to report to federal highway of the number of different types of vehicles on the roadway, so this could help them do that. Are there any other questions? All right, we'll skip that. Here's one example of a 3-axis magnetometer. This one is made by Census. Its sensing area is about the same as that of a 6-foot loop. And these can take less time to install than, say, a square loop. Here you just have to core about a 4-inch hole. You drop in the magnetometer, align it properly, and seal it in with some epoxy. And it runs off a battery. It transmits its data to either the roadside cabinet or to a repeater module that can transmit it further down the roadway. There's a second company in Minneapolis that makes a magnetometer. And this shows what that unit is.
I'm obligated to mention that Census Networks was founded by Path
Yes,
founder
yeah.
Raveen Baraya. So
Yeah.
an example of entrepreneurial efforts coming out of the Senate.
Sitting there. Okay, magnetometers give you similar data to the loops. They are embedded in the roadway. Again, they have a low per unit cost. They are wireless. And they can detect small vehicles, even the bicycles, and arrays of magnetometers may provide vehicle classification with the proper software. But they too have their limitations. You have to interrupt traffic to install them or to repair them. If you have closely spaced vehicles, they may not be able to discriminate between the two vehicles. When you have a curve or a curve in the roadway or a wide lane, you might need several magnetometers across the lane due to lane stragglers. There have been papers written about this. I finished talking about the sensors that I'm going to install in the roadway. It's time to talk about the over roadway sensors. So I've got my friend Bugs here. There are times when he plays his theme song, but he didn't want to do it this time. The first of these non-intrusive sensors are the video detection systems. There are lots of these that are made. I've just shown you a few from 4 companies here. They're made in the US, they're made in Europe. On the upper left are some made by Terrace. Oops, I don't want to do that. Which is the point. There it is. There are some shown by the superscript A that have multiple technologies, video and presence detecting radars. So they make 1, 2, 3 of these that are dual technology sensors. This is a bunch made by on the upper right are the sensors from Teledyne FLIR in Belgium. On the lower left are those made by the folks that bought out Peak Traffic. And on the lower right are the Autoscope products. All right, now I'll add that. One of the questions that comes up here is at what distance can a video detection system distinguish between closely spaced vehicles? And this slide shows you how to calculate that distance based on the vehicle height, the camera mounting height, and the inter-vehicle gap. So that's just something to help you figure out, how close vehicles can be when you can see 2 separate vehicles rather than one larger one. See, I think that there's something else here. Although some manufacturers quote a maximum surveillance range of 10 times the camera mounting height, there are more conservative procedures that limit the range to smaller distances due to factors such as the road configuration, such as elevation changes, curves, overhead or underpass structures, the level of congestion, vehicle mix, and inclement weather. There are 4 general guidelines for installing a camera used with a video detection system. And here they are. The first is you want to maximize camera height for the most accurate data. You want to select the camera location to avoid or minimize occlusion. You don't want to include the horizon in the camera view. And you want to use the sun shield to minimize sun glint on east-west facing cameras. Are there any questions? Here's that summary slide. There's a rich array of data you can get from video detection systems. Once I was good at pushing buttons. It's shown in the upper part here. Count, presence, lane occupancy, speed. You could get, advanced detection zones and queue length. With a video detection system, they come with software that allow you to set up the detection zones for different applications, and that's what leads to this rich array of data that is available. The advantages are a single camera and processor can monitor multiple lanes. Here I'm talking about freeway applications. If you're looking at traffic signal control applications, usually there's one or more cameras for each direction of traffic flow. You can change the configuration of the detection areas. They have, the video detection systems have limitations. Some have decreased over the years as the cameras and the processors have gotten better. Large vehicles are known to project their image into adjacent lanes, causing false detections. Large vehicles can also mask vehicles in lanes further from the camera if you have a side mounted camera. A video detection system's operation can be affected by shadows or reflections from wet pavement, day to night transitions, headlight beams, and so on. So for a first time use of a video system, I think it's a good idea to test out the system, make sure it will work in the area and in the weather conditions that it will be subject to. There have been studies that show that reliable nighttime signal actuation does require a well-lighted intersection, and high camera mounting is needed for more accurate data. One way to get around the need for nighttime lighting is to go to a thermal imaging camera. These are made by FLIR, so they can see in darkness or poor lighting and through some smokes and light fog. I don't want to take. Yeah.
What's the accuracy for the speed measurement from the video?
It's pretty good. It's in the 90s. But again, the manufacturers don't tell you if it's a 1 sigma, 2 sigma. Usually it's 1 or 2 sigma, it's not 3.
How often do they usually update the output?
The what? The software?
How frequently they can output the speed measurement?
You get per vehicle data. You can get per vehicle data.
Per vehicle, like if a vehicle passing through an intersection, I get one data point for that vehicle or a segment of the points indicating the speed trajectory.
Yeah. Some of the video systems, all of them don't track vehicles. Some that do, and they will give you some can give you a trajectory. You show you turning movements, lane change movements. But you have to look at the individual models. I think, were you able to send out some of those papers that I sent you? Did you get that email with a couple of?
Not sure I did. I'll check it and
I wrote a couple of documents. One was maybe 4 or 5 years ago. That's about 30, 40 pages that may have some of this information. And then last summer, I had a paper published in the IEEE ITS magazine, which updated the hardware, but I was more page limited, so there's not all the information in there that was in the earlier report. But I can leave you a copy of the slides, and those two documents are available. So this is vehicle detection and sightless detection with an IR camera. It works in the long wavelength region. There are some websites here that will allow you, I think, to play that. Maybe it's a video. This first website might be a video of the vehicle and bicycle detection. And you can get similar data to that of a visible spectrum system. And again, it can operate when your lighting is poor or in some smokes and fogs. These cameras operate at 30 frames a second. Let's see. Okay, the next group of sensors are the microwave presence detecting radars. And I have several of these. Again, there are many more out there. This is the RTMS Echo, and here they added a camera so that you can view the scene and confirm the presence of vehicles. And you can see that here I gave you some more detail. You get per lane data, you get per vehicle data. And this was done to meet new federal highway reporting guidelines. So several of these radars give you the per vehicle data. This is the smart sensor by Wavetronics. Again, you can get per lane and per vehicle data. This is a radar made by a company in the UK, AGD. They make lots of models of radars. Some are adapted for limited access highway, and some for signal control, some for pedestrian detection. This is a unit made by Iteris for stop bar and stop bar detection, signal control. And then this is a German radar. I'm here, their specs didn't say specifically whether they gave you per vehicle or well, per vehicle data, but they may now.
Excuse me, for these radars, if you wanna instrument an intersection. I don't know if you can give me guidelines for like, how many do you need? Do you need just one for each approach, or do you need like, multiple to get it, depending on how many lanes you have? Or...
Yeah. I would think you need, if you're looking for opposing traffic flow, there's a possibility one might be able to see both sides of the street there. Let's see, this Vantage says it can do up to 22 lanes. So it depends on the antenna type, say, on the processing they have. They do vehicle classification. It's limited. Usually the vehicle classification is by length, by vehicle length. For a specific question, it's best to call the vendor or their representative. These models change every few years. Software could be upgraded. The Doppler sensors don't detect stopped vehicles. This is one made by AGE again, and it has its applications. The Doppler sensors are popular for wrong-way vehicle detection. Here's one made by a Swiss company, ADEC. And then there's the icon that's used in work zones to identify the speed of vehicles and coming towards a work zone. Doppler sensors transmit a constant frequency signal, and then the received signal, if the vehicle is coming towards the sensor, will be greater. If the vehicle's moving away from the sensor, the vehicle will be less than the transmitted signal frequency. The presence detecting radars usually transmit an FMCW signal, and the difference in the transmitted and received frequencies is proportional to the range, to the vehicle, or to the detected object. I want we're going to run out of time here. Again, there's the summary chart. Again, there's a rich array of data that you could get from radars, especially the ones that detect stopped vehicles. They are installed overhead. They can either be forward-looking or they can be mounted at the side of a roadway, depends on the application. If they're mounted at the side, then installation and repair need not interrupt traffic flow. They give you a direct measurement of speed. You can get multi-lane data, and like the video systems, you can reconfigure the detection areas, and they operate day and night in inclement weather. Again, they have their limitations. With side mounting, once again, there's a possibility of misdetections of vehicles in lanes further from the sensor. Vehicle undercounting can increase in heavy congestion. Radars have a setback mounting distance from the first lane that you want to monitor. You have to make sure you take that into account. And then radar detection is a stochastic property. Usually you don't have to worry about this. The manufacturers have taken that into account, but that means that it's a random event. So the radar can miss a detection opportunity, or it might detect a false object as well. Okay, LiDARs. So the applications of LiDARs seems to be increasing every year. When I first started in this field, there were just a few of these over roadway mounted sensors. These are still made. They were used to classify vehicles mainly. They could measure vehicle speed and things like that. This model has a scanning mirror, which scans the beam, or it scans a laser diode beam, a near IR beam across the lane. This is a company in California. The next two are made by a German company. This is a unit that's made to monitor one lane. This is a multiple unit system that can monitor up to 4 lanes. It classifies vehicles, pretty high accuracy for classification, 96%. Yes,
Do you know how much those cost on average?
a lot. I think in my papers, there are some cost figures, I forget, but they're They could be over $10,000 or 20, you know. I'd say between $15,000 and $20,000 for, whoops. For the ones on the top, you know, this one probably costs more. Yeah,
So can they also detect how many people are sitting in the same car?
I don't think so. Not these, I think you want to use other wavelengths for that. Yeah, they are not used for that, just lane occupancy, not vehicle, personnel occupancy.
Do you know what type of sensors can detect the vehicle occupancy?
There are IR sensors that have been tried.
Okay.
I used to know of a couple of companies that made those. I am not sure that they still make them. Yeah, so the unit that was on the upper left scans its beam with a rotating mirror, and this gives you that concept. The ones made by SICK scan the beams again with a rotating mirror, but they calculate speed slightly differently. Again, you can get all this information by speaking to the company representatives. They're quite helpful. They want to sell you their products. Okay, there's another set of LiDAR applications. There are more and more of these applications to intersections. Typically here, there's a LiDAR, usually two LiDARs. It depends on the size of the intersection and the number of approaches, but they're hung overhead. They scan the intersection. They can detect stop vehicles, turning movements, bicycles, and pedestrian movements. This is an example of a system in Salt Lake City that's being tested by Utah DOT. Is there a way to click on that video? There could be an ad that comes up from here. Maybe you can
Get out of the.
Oh, and Opus opened it in a different window.
Oh. I can try from here and see something. Anyway, what that video shows is you can see vehicles in the camera view, and you see their movement from the output of the LiDAR on the right side of the screen.
There was a short glimpse of it on the Zoom screen share,
Yeah.
so folks can go
But I
back
did
to
it,
the
I did it
recording
differently.
Okay.
and check it.
All right, how do I go to the next one? Next screen, please.
Cool.
Okay, here's another one. This is made by another company, Ouster. It's being used in Chattanooga, Tennessee. Next slide, next clip. And they started with 12 intersections. They're expanding to 130 intersections. And again, there's a video here. I don't know if you can start that one.
If I,
It's in red up there.
yeah, if I click on it, it opens in a different window and then I have to drag it over. It just takes a minute. See.
You know, every time I read some industry magazine is another example of a LiDAR system being applied to intersections or vehicle classification. So it seems to be becoming quite a popular way. Prices are probably dropping for these systems. Yeah. So this movement represents people. These are detections from the LiDAR system. Now, again, this is from the manufacturer, not an independent testing agency. We can go on. Sure. All right. That is over there.
Yes, thank you. Alright, did it change everything?
Yeah.
Okay.
Perfect.
Oh, you need me to advance, sorry.
Next slide, please.
Yes, thank you.
Okay, here's a third system, a third LiDAR. This is used for vehicle classification, not for signal control. So you can see that they claim a very high shape classification accuracy. Includes car, van and pickup are one category, truck, semi-trailer. Next slide, please. Again, here's that summary slide. Typical output data from a LiDAR sensor. They're installed either overhead or to the side of the roadway, depending on the application. They can operate day and night. There are some models that cover multiple lanes. Their limitations are if they're installed overhead, again, you have to interrupt traffic flow. If you have heavy fog or blowing snow, where the visibility is less than about 20 feet, LiDARs may not be able to work since the lasers operate in the near IR. So a rule of thumb is if a human can see that distance that a sensor is mounted from the roadway, then the LiDAR will work because the human eye visible range is similar to the near IR spectrum. So if you can see it over that distance, then the LiDAR will work. The mean time between failures is adequate. Some of the systems that have the rotating mirrors scan at slow speeds than others, so they have a longer mean time between failures.
Does LiDAR, it seems like LiDARs do not have occlusion problems.
Occlusion, well, if they're mounted at the side of a road, say.
It's the weekend. What are we doing?
Oh,
Come on.
that's,
Relax on the walk. That was exciting. Excuse me.
focus up.
By the way, we have just about a minute left.
Yeah, I am almost done. Yeah. If they're mounted over the roadway, like in the middle of an intersection, there's very little occlusion. It depends where they're mounted.
I see, that just like the radars and the video cameras, right?
Yeah,
The same.
okay, next slide. What can I do? Okay, these are two sensors that use multiple technologies. The one on the left is IR and ultrasound. the one on the right is IR, Doppler, and ultrasound. What are the takeaways? All of the technologies I've talked about and the others that I didn't talk about have capabilities that meet present day applications. Many of them give you individual vehicle data, especially the video and the radars. Sensors being considered for a first time application should be evaluated under the anticipated operating conditions prior to buying them on a large scale. Loops and video seem to be the dominant technologies that are used for signalized intersection control, although presence detecting radars are developing capabilities that can make them useful for this application. Magnetometers appear in signal control, vehicle count, ramp metering, parking applications, and limited access highway data collection. Next slide. Evaluation of sensor costs must account not only for the purchase, but for software and updates, training, software initialization and detection zone setup, any cables, installation costs, first time use testing, data transmission costs, maintenance and other costs associated with implementation of lane closures, safety measures, and environmental hazard mitigation. They should also have to include preparation of road surface or subsurface for the intrusive sensors and any required mounting structures or power sources for the non-intrusive sensors. And finally, the last second, yes. Oh.
So, all right. I'm a country in the global south or a developing country. I haven't bought any of these yet, and maybe I have very limited, signals anyways. So if I just want to know, okay, what's going on in my country? How much are people driving? Maybe I want to do some very limited, control and say by city centers. What do I do? Do I buy any of this stuff, or do I require everyone who's wealthy enough to buy a car? You just put some beacon in there that tells me where.
Yeah, now that's a type of sensor I didn't talk about. You can buy data from commercial sources that will come out and install sensors, and you pay them for the data. So, these days, you can pick up the the Bluetooth signal.
Sure.
From vehicles with readers, and you could get data that way. You could get origin, destination data, you could get count data. I don't know if anyone is using that to control traffic signals yet. That might be a future application of the Bluetooth data.
But what would be your recommendation to developing countries? Like,
Do you have power there? I don't know what you have there. What's the climate?
Assume it's India. You have power, it's hot and raining.
Yeah. So you might want to stay. If the rain is monsoonal, I don't know if the video would work. You could try the imaging IR, the FLIR sensors. You could try radars. You could try magnetometers buried in the ground. Or by the same token loops. I don't know which would be simpler or lower cost. Again, it depends on the condition of the roadway. If you don't have good roadway, you don't want to put in loops. They just won't hold up. Maybe the magnetometer will hold up better. I would not probably play around with the ultrasonic or the acoustic. You know, there are other, so. After this are the slides I didn't show. So there's a whole bunch of these magnetic sensors that have been around for decades. They don't detect stop vehicles. But if you want to count vehicles or something, you bury them under the roadway, either you drill a slot, you drill a hole and you insert them, or you core a hole and you drop them in, but there's a whole group of these things. This is a video system again. Anyway, there are more slides I just didn't show.
This was great. I mean, this was, I think, an excellent tutorial of all the different sensing technologies presented in such a structured way. So, you know, and that the whole lecture makes me think of, you know, in Spanish, we say profe, you know, professor, very educational. So thank you, profe Klein.
Thank you. It was my pleasure to be here, and thank you for inviting me.
Great.
Thank you.